Great.
So hi, everybody. So the reason why we are doing this joint what is dynamics is because this idea is to advertise a seminar that we want to do, a students learning seminar about dynamics. In this what is, you will see two ideas in dynamics, one of them that I will present and another one that Eran will present, and they are very diverse ideas. And there are plenty more ideas. If you want to talk about these ideas or learn about them, please join us in our learning seminar and we will tell you more about this later. So Eran, take it away and begin this what is, the last what is of the semester.
Okay, so welcome everyone. To begin my part, so what are dynamical systems? Dynamical systems are, in a sense, a mathematician's attempt to study the abstract notion of evolution with respect to time in nature. Now, this is, of course, a not very well-defined concept. So, before we introduce the definition for a dynamical system, let's consider the following example. Okay, let's assume we have some vector field defined on, say, Rn, or let's say even a manifold, and let us also assume that vector field is sufficiently smooth, so whatever I'm about to say actually holds. So from now on, we'll refer to the collection of all possible solutions to the system of ODEs defined by that vector field as a flow. Why a flow? Because in a sense, we can think about it as, say, the motion of particles through, say, a river, okay? Now, a solution within the flow is said to be periodic, provided it is some closed loop. Here you have a more abstract definition, but essentially all it tells you is that our periodic solution would be some closed curve. It may, of course, intersect itself. It may also, well, it does not intersect itself, but it may link around itself and so on. So, flows are, in a sense, a very good example of a dynamical system. Why so? Because when you think about it, they can be used to model evolution with respect to time. For example, say, the location of particles in the air or the ocean. However, there are many other dynamical systems. Not all of them can be represented as flows or differential equations to begin with. One such example, which actually arises from flows, is the iteration of functions from space to itself. To begin explaining this example, let us first consider the motion of objects which lie on some fixed distance from the Earth. We can, of course, think of that motion with respect to those objects as some flow on a torus, right? Great. Now, as we all know, the existence and uniqueness theorem, while it does guarantee the existence of a given flow, it does not teach us a lot about it. Why so? Because the existence and uniqueness theorem, while it does present us an algorithm to compute the solutions to ODEs, basically, that algorithm is not very useful when we need to analyze specific systems. And this led mathematicians such as Henri Poincaré to try and study such flows qualitatively without resorting to analyzing vector fields. And one of that method was Poincaré's first return map. Now, what do I mean by a first return map? If we go back to the slide with the torus we had earlier, yeah, thanks. Let us take some cross-section which is transversal to this torus, okay? And let us also assume that all the trajectories which pass through initial conditions on that cross-section cross the cross-section transversely, that is, they pass through it, they're not tangent to it. As an illustration, what I mean is that the solutions must go through the cross-section. They cannot be tangent to it, okay? Great. Now, assuming that any initial condition on that said circle would eventually return to this cross-section, we could derive a circle map, correct? We could simply ascribe a given point x 0 its first return point on the circle. That is, x1, which we correspond to x0, would be the first hit for the trajectory of x0 once it leaves the section. Is this idea clear, or isn't it? Great. So this, in a sense, can also be used to generate a dynamical system. And why so? Because if we consider the functional sequence Fn, with Fn denoting the composition of F with itself n times, then studying the trajectory of a given initial condition x0 under this sequence can also teach us how the system evolves with respect to time. So, having said that, if we wish to give a formal definition for the concept of a dynamical system, then we need some definition which captures both these notions, both that of a dynamical system generated by a flow, as well as that of a dynamical system generated by a function f from space to itself. So how can we do that? We can, when we give such a definition, we would like it to be constructed in such a way which would allow us to study the future of a given system. Why so? Because, after all, when we analyze dynamical systems, we would like to say a few things about the future of given initial conditions, that is, how they evolve. So, are there any suggestions for a way I could define such a dynamical system before I hand you the definition itself? No.
Maybe use the periodicity.
Oh, sorry.
Never mind.
Wait.
Never mind.
So we had a suggestion.
Okay, so in order to define a dynamical system, we need two objects. The first is X, which is some set. It may be Rn, it may be some discrete set, it may be a set of matrices, it can be whatever, to which we refer as our phase space. That is, this is the set within the system evolves. The second step we're going to need is T, which would denote our time semigroup. And a dynamical system would be defined as a semigroup action of T on X. Why a semigroup? I guess some of you are probably wondering. Well, the reason is that many dynamical systems are not necessarily reversible. For example, take a polynomial which acts on the real line. It cannot define a reversible system, and as such, if we allow T to be a semigroup instead of a proper group, then we can be a bit more flexible when studying this theory. Now, for example, as we've seen, a flow is an example of a continuous time dynamical system in which the trajectories of given points are simply paths in our phase space. The reason being that T in that case is simply the real line. However, given some function from space to itself, say a first return map, but not necessarily, T is some discrete subgroup, for example, either the natural numbers or integers. So this is an example with which the time is discrete in a sense. So at this point, I think I better let Noy introduce the basics of one very special type of dynamical systems, which is the most minimal.
Okay, so hi everybody. So now I will talk about Eran.
Oh,
So now I will talk about circle rotation. So in my case, I look at a circle as R mod Z. How do you see it? You see it like this. So this is a circle. It's also isomorphic to 0, 1, which is a quotient space of R mod Z. Why so? Because every number can be written as a number in Z plus some number in 0, 1, and then instead of saying that I want to look at 0, 1, I could just look at something like this. I could just take the two ends and connect them together. Next. Okay, so now we look so now we can define a map T alpha from T to itself, which is a circle, by T alpha of X is X plus 1 mod alpha. So in the picture, this is, let's say 0. This is alpha, the angle. So it goes, this is alpha. Here you go to 2 alpha and so on and so forth. Okay, so now let's understand how this acts for a rational alpha. If alpha is rational, then there is some n such that n alpha is equal to 0 mod 1. Why so? Because you could take the n to be the denominator of alpha. So now, if you look at it, what happens if you take t to the n, t alpha to the n of x, and that's going to be equal to x plus n times alpha. But then that is just going to be equal to x mod 1. So now in this way, we could look at the orbit under T alpha of X. So this orbit is going to be X plus, and this orbit is defined as T to the N alpha X, where N is greater than 1, but it just is going to be X plus alpha, X plus 2 alpha, up to X plus N minus 1 alpha, because when we get to N alpha, we return back. So this orbit is finite. In a way, this behavior is very, very strange. We want to say that this is a behavior that isn't very common. And moreover, we would like to say that that basically we want behavior where it equidistributes along here. That means that if you take infinitely many n, then it should eventually, we want to say when does it eventually equidistribute, like 1 over n points that are 1 over n points that are 1 over n separated. So this is a notion which we shall call ergodicity. Now, okay, next. Now, to define an ergodic system, so we first have to define a measure preserving system because ergodicity is a property of measure spaces. Thank you, Dany. So we say that T from X to X is measure preserving when X is a space and T acts on X in the following, if the following holds. If for every A in X that's measurable, the measure of A is equal to the measure of T minus 1A when T minus 1 is the inverse image under T. Moreover, we say that a measure-preserving transformation, T from X to X, is ergodic. If T minus 1A is going to be equal to A, that implies that that A is either a set of zero measure or a set of complete measure. That means that the only invariant sets have this type of rigidity in their behavior. Now, let's understand what does this mean. I said earlier about distribution. So if you remember, when we have a rational point, a rational rotation T alpha, when alpha is rational, then the orbit distributes on finitely many points. No matter how large n is, the orbit is going, if you take T to the N alpha, where n is from 0 to some very, very large number m, then the orbit is still going to distribute on at most n points. But now, when we have something called the Pointwise ergodic theorem, which says that if our transformation is ergodic, then the orbit will eventually equidistribute. That means that when we have a very, very large number of points m, then the orbit will distribute more or less uniformly. And this is exactly what it says, that this limit here, if you take any function that is nice, evaluated at T to the nx, and then you divide it by the number of points that you're evaluating at, it should go to the integral of the function with respect to the Lebesgue measure. And this is exactly what it means that it's uniformly distributed. So now let's understand, now that we have this property of distribution, let's understand the orbits. So let's add some topology to the space. If we have a space that's topological as well as a measure space, and it's a probability space, that is that the measure of the entire space is 1, and let's assume that T is a measure preserving transformation. Now let's look at the orbit under this. So the orbit is this thing here. The orbit is simply these points. Now, we notice that if you take T to the N of Z, where T to the N of X, where N is in Z, then this is T invariant. Why? Because if you take T to the -1, then you just simply move every index back by 1. So if T is ergodic, then every orbit closure must be of measure either 0 or 1, in addition to the fact that the orbit distributes well. Now, another question that we can ask is what happens about the orbit, about topological properties, like is it dense, for example? So first, let's look at this next. Keep on going, you're going backwards.
Next.
Okay, next. Okay, so now let's talk about the circle rotation and ergodicity now that we've understood a little bit what does ergodic mean. So the circle rotation, we can say that if alpha is irrational, then the circle rotation is not ergodic. That we saw because the orbit distributes on finitely many points. On the other hand, if alpha is irrational, then this is ergodic. A way of showing this, for example, is by using Fourier coefficients. I will not do this, but anybody who is highly ambitious or knows a solution can do this at home. Now, the next question is, when are these orbits dense? So firstly, let's understand what does this mean for an orbit under the circle rotation to be dense. So the circle rotation, you basically say that x plus n alpha mod 1 is dense. What does this mean? This means that x plus n alpha, go on. Okay, so let's first understand when this contains 0. So in order to understand when this contains 0, then it contains 0 if and only if x plus n alpha is arbitrarily close to 0 mod 1. Another way of saying this is that x minus n alpha, I just changed n with minus n because it's equivalent in a way, is going to be x minus n alpha is arbitrarily close to 0 mod 1. That means that x minus n alpha is arbitrarily close to an integer, meaning that for every epsilon, there is some n such that if we denote this by the distance from the nearest integer, then x minus n alpha is going to be smaller than epsilon when you denote this as the distance to the nearest integer. Next. So let's understand what happens when we choose specific epsilons. Like what happens when we take epsilon n equals 1 divided by n. And on purpose, I have the same n in both of them. So now this goes to the theorem of the theory of Diophantine approximation, which is how do you approximate numbers by fractions. So a theorem by Cassel says that if you have an irrational alpha, then for Lebesgue almost every theta, there exist infinitely many n, such that n alpha minus theta, the distance of that from z, is going to be less than 1 divided by n. Now, the question is, can we do any better? In a way, you could say that what this theorem says is that n times n alpha minus theta, z, is going to be less than 1 infinitely often. So this says that this thing here is going to be infinitely often less than 1. Can we say that it's infinitely often very, very small? So let's see what this says. So it says, so you can do a lot better. That is, for almost every alpha and theta, you have that this lim inf goes to 0. That means that you can find n such that this guy here is going to be arbitrarily small. Now let's understand what does this mean. So firstly, this can be generalized for vectors as well. A way to see this for vectors is that now we have alpha, which is a vector. Let's say alpha is alpha 1 up to alpha n, and theta is theta 1 up to theta n. And now we ask, can we find n such that n times n alpha I minus theta I is going to be simultaneously less than, is going to be, this lim inf is going to be simultaneously m0, lim inf, and this is going to be of the maximum of the I. And as it turns out, this can be done. So now, go back 1 second and then go forwards. Okay, so now we said that for almost every alpha and theta, we have that this lim inf is 0. But we are good mathematicians. As good mathematicians, we are not just interested in what happens in nearly all of the cases. Rather, we are also interested in the set of exceptions. That is when this does not happen. And this is what's called badly approximated vectors or numbers. So I'll go straight to the vector case. So we say that a vector alpha in RD is badly approximable with respect to theta if there exists some epsilon. I'm just basically doing the opposite of this definition. If you could find some epsilon such that for any n, the maximum of the coordinates of n times the distance of n alpha I from minus theta I from z is greater than or equal to epsilon. So we know that this set is of measure 0 because we've just talked about it if alpha is irrational. And let's call this set here the set of vectors that where this happens, let's call this bad theta. Now we know that this set for any irrational is going to be of measure 0. Now let's see what else we can say about it. So it's of measure 0. Can you say how large it is? We know how small it is. What about dimension? There's a notion of dimension, like RD is of dimension D, R is of dimension 1, and then there's weird sets like the Cantor set, which have some fractional dimension. What can you say about the dimension of bad theta? Turns out it's a set of dimension D, which means that it is small, but not very small. What other notions of largeness or smallness do we have in these spaces? You have another notion, which is called Schmidt-Winning. It means every set that is Schmidt-Winning is going to have Hausdorff dimension D, but it could have Lebesgue measure 0. So it turns out that theta is bad theta is Schmidt-Winning, and this is kind of surprising in a way because you'd expect that a set of 0 measure should not be Schmidt-Winning. I won't get into what it is, but this is another reason why you guys can come to the seminar to hear about this. So now another thing that you could look at is we talked about numbers, we talked about vectors, which are generalizations of numbers to multiple dimension. Now you can talk about matrices, which you could view as a generalization of vectors. So as it turns out, we can talk about the badly approximable matrices in some way. So these badly approximable matrices, they have measure 0, they have Hausdorff dimension D, and they are also Schmidt-Winning. There's a lot and a lot more when it comes to Diophantine approximation, like instead of approximating with n times this, you could approximate with n to the power of some different number like beta and see what happens. So we said earlier, this is a talk about dynamics. So I would like to connect between approximation and dynamics, in particular, a field called homogeneous dynamics. There's 2 ways to connect between these. One of the first ways is the following. You'd say that you could view these functions here, or these ones here, you could view them as functions on lattices. And then and lattices, they come from homogeneous dynamics, because in homogeneous dynamics, we look at how matrices act on lattices. So you could ask about, so this is one connection. Another connection, which goes back to how many of the previous theorems that I mentioned were proved, is due to a result called Dany Correspondence, which connects directly between homogeneous dynamics and Diophantine approximation. I would like to explain what Dany Correspondence is, but to do this, I have to explain a little bit about the setting in homogeneous dynamics. So we want to talk about the space of lattices. So a lattice, you could look at it visually in a way. A lattice, let's say in R2, it's going to be something defined by 2 vectors. Let's say this vector and this vector, and it's going to be closed under multiplication under Z, and it's also going to be closed under summation. So you could say that it's a full Z module even, in a way, and this is how you could envision it to look like, as a discrete set of complete dimension. Now, we have an algebraic way of looking at a lattice. A lattice algebraically, you take some matrix of determinant 1, and then you multiply, and then you look at it acting on ZD. So this here defines a lattice, and we can identify the space of lattices with a space SLDR mod SLDZ by GZD goes to G gamma, where we say that gamma is going to be SLDR and G is SLDZ. So this is how we can view the space. Now let's talk a bit about the setting. So as we said earlier, G is SLDR, gamma is SLDZ. Next. So now let's understand how G acts on XD, because I said matrices act on lattices. So G acts on XD in the following manner. You take a matrix H, it acts on the lattice G gamma by H, takes G gamma to H G gamma. So it basically translates the lattice with respect to a matrix H. So now every lattice, let's say this lattice here, you could view it geometrically as well. So as a geometric item, it has vectors. Of these vectors, there is a vector that is of shortest length and is not 0. Let's say in this case, it would be this vector. So let's call this, if this is our lattice, L of L, alpha of L. This is going to be the length of the shortest vector. For example, if you take the lattice ZD, who knows what's the length of the shortest vector in ZD? 1, great, because the shortest vector is E1 or E2 equivalently. For example, if you take the lattice half E1 that's spanned by half E1 and twice E2, then the length of the shortest vector is half. So now we want to define some sets here. So now that we have the length of the shortest vector, it turns out that we can use it to define sets. In particular, we have these sets here, K epsilon, which is the set of all of the lattices in XD, such that the length of the shortest vector is going to be greater than or equal to epsilon. Now, Muller's compactness criterion, which comes from geometry of numbers, claims that every closed set in the space of lattices is going to be compact if and only if there exists some epsilon such that C is contained in some C epsilon. That is, in order for a set to be compact, it has to be closed and the length of the shortest vector cannot be too short. That is, it has to be bounded by below. So for instance, here is an example of a non-compact set. Let's take this guy here, the lattice spanned by these two, and then after that, the lattice spanned by these two, and then you just keep on making this part shorter and this part to be longer. And that is not going to be compact, for example, because the length of the shortest vector is going to be this here, which goes to 0. Now we have all the tools we need to define Dany correspondence. So remember in Dany correspondence, we had alpha and theta. So for alpha and theta, let's define two matrices. The first one is going to be an upper triangular matrix. U alpha of theta is going to be ones on the diagonal. And then this here is going to be the vector, which is given by alpha as a vector of as basically a column vector, and then minus theta as column vector. And the second matrix is going to be the diagonal matrix, which has d times t to the t over d on the diagonal, and then it has 1 time e to the minus t, and then once 1. Everybody can verify that these matrices have determinant 1. Now that we have this, Dany correspondence says that alpha is in bad theta if and only if there exists some epsilon greater than 0, such that for every t, if you project, so let me explain what this is. The projection of this flow, AT times U alpha theta of ZD plus 2 on the first V minus 1 coordinates is going to be in K epsilon. So let's understand what this says exactly. You could look at U alpha theta times ZD plus 2. This is a lattice in ZD in ZD plus 2, D plus 2 dimensional lattice, and then on it, you act by some diagonal matrix, some diagonal flow. And then after you do this, you project to the first V plus 1 coordinates. So once you do this, if all of this is going to always belong to some fixed compact set, no matter how large you take T, then we say that the vector is badly approximable, or in other words, that it is going to be, far relative, that the series N alpha is going to be relatively far from theta. Now, using Dany correspondence, what we would do, for example, to prove many claims about dimension or winning properties of badly approximable sets is that we would use Dany correspondence and then prove these claims using tools in homogeneous dynamics, prove this with tools of homogeneous dynamics, and then after that, use Dany correspondence to go back to say that alpha must be in bad theta. So this is our connection. Now, I would like to say a few more words about homogeneous dynamics. So as I said earlier, it's a study of actions of subgroups of SLDR on the space of lattices, SLDR mod SLDZ. Next. Okay, so let's talk about some of these subgroups. Some of the subgroups that we have, as we saw, are the diagonal group, the group of diagonal matrices with determinant 1. And another one of the subgroups is going to be what's called the unipotent group, which is basically the group of upper triangular matrices that have ones on the diagonal. Now, let's talk about some interesting questions in homogeneous dynamics. So some questions that we are interested in is, given a subgroup H of SLDR, how do the H orbits or orbit closures behave? Can we say anything about them? Are they dense? Which orbits are compact? How can we classify them? Moreover, given an H orbit, HL, let's say, or the closure of HL, what are the H invariant measures supported on these orbits, or do any of these exist? Are there any measures that are invariant under other groups? Now, another question that we could say is, given a sequence of H orbits, let's say H times Ln, and let's assume that every one of these orbits supports an H invariant measure, then what can we say about the limits of such measures? Can we say that they converge to something? What type do they converge to a nice measure, like something kind of like the Haar or the Begg measure, or do they converge to zero? And another question is, if we go back to the Pointwise ergodic theorem, how do averages along H behave? What does that even mean? And also, when is the H action ergodic? So these are all very deep questions that there are lots and lots of papers about, and it's a very, very large field, and we would love for you to hear about it more in our seminar. But right now, what I do have time to explain is a little bit about the orbits of the diagonal group. So firstly, a very nice thing that we can see about orbits in general is that since A mod the stabilizer of A is going to be equal to AL, this is basic algebra by the orbit stabilizer theorem, then an A orbit is going to be compact if and only if the stabilizer is not small. Moreover, this happens if and only if the stabilizer is of the same rank as A. That is, it's a lattice in the diagonal group. Now, another thing is that AL is compact. We can also talk about compact orbits. So AL is compact if and only if L arises from a totally real field embeddings. So an interesting question would be, which field embeddings. It would be studying field embeddings. Like, let's say if you have a field extension, then what are the lattices that it forms? And the other way around. So this connects oftentimes between Galois theory or number theory and homogeneous dynamics. And another thing is that A acts ergodically on XD, and therefore there are dense A orbits. So we said that there's dense A orbits and compact A orbits, but there are orbits that are not compact or dense. For example, the action of the diagonal group on ZD is not dense or compact, and you could kind of envision it as being all of the lattices that are formed by vectors on one of these two axes. So this is not going to be dense or compact because it doesn't cover a lot of more lattices. So this is going to be my part for now. And now I would like to bring Eran back to the stage to give us a very different approach. So here you go, Eran.
Yeah, thank you, Tali. So, as we've just seen, considering dynamical systems with very minimal requirements, such as that the function generating the dynamics is measurable, yields a very rich and interesting theory. And these questions also lead us to other questions in which we would like to know what happens when we assume something stronger, say continuity or even differentiability. That is, this time, we assume our dynamical systems are created by, say, differentiable functions. So, as it happened, when scientists first began analyzing dynamical systems, they first analyzed, well, continuous and relatively well, and the dynamics of relatively well-behaved function. The reason being that these were the functions they often encountered in applications. However, as they did that, they began to notice many strange phenomena. For example, that many such dynamical systems contained dynamically invariant subsets, by which I mean subsets within the phase space, which are mapped by the dynamics into themselves, such that those invariant subsets had very strange geometric structure, and also the dynamics on them were just as complicated. To illustrate this idea, let's consider the following example due to Lorentz. So let's consider the following system of ODEs, which, as you can see, depends on 3 parameters. This system was originally discovered by Lorentz, I think, in 1963. And he originally derived it after studying the convection of air with respect to the surface of the oceans. Don't take my word for it, though. I'm not a physicist. But anyway, the interesting thing about this example is that Lorentz observed how at these parameter values, the dynamics were chaotic. What did I mean by that? He observed that any 2 initial conditions he chose, no matter how close they were chosen, eventually diverged from one another when he let time go on. To be more precise, what Lorentz actually proved was the following thing. He proved that any 2 initial conditions in R3 were eventually attracted to this butterfly-shaped figure again in R3, and that when those orbits were sufficiently close to this set, the orbits diverged from one another. However, not only these orbits diverged, they also, in a sense, came back together only to diverge again, and this aperiodic behavior simply kept on going for infinite time. And this led Lorentz to publish his findings and describe this type of behavior as chaos. Now, when Lorentz first published his results, at first mathematicians did not really consider them, and the reason being that this was, after all, nothing but an example. However, as the years passed on and more dynamical systems were studied, mathematicians and scientists began realizing that chaotic dynamics were, in a sense, the rule. And what do I mean by that? I mean that most of the dynamical systems they encountered contained such intricate invariant subsets on which the dynamics were extremely complex. Now, at this point, since we are mathematicians, I think it would be best to give a definition for what I mean when I refer to chaotic dynamics. So, let us assume we have some dynamical system, which is defined on some space X. We say it is chaotic, provided the following conditions are satisfied. First, that there is a dense subset of periodic trajectories within the phase space. Two, that for any two open subsets, A, B, and X, there exists some positive number such that the iterate of one set A intersects with B at some point. Or in other words, any two open sets in our phase space would eventually mix together. The third condition, which as you probably observe is relevant only when X is metric, says as follows. It basically claims that there exists some delta such that for every X in X and every positive radius, there exists some Y in the ball of radius R around X and some time in the future such that the orbits of X and Y diverge from one another at that time. Now, it turns out that the third condition can be dropped. What do I mean by that? I mean that in 1992, two mathematicians whose name I've forgotten managed to prove that the third condition can be implied by the first two, which allows us to basically extend this definition to, a more abstract topological space. Okay? Now, another question which bugged, and I guess still bugs many scientists, is why do such complex chaotic dynamics and fractals often appear in conjunction? For example, we have already observed the Lorentz attractor, which, as we've seen, does have a rather complex geometrical shape. However, complex geometrical shapes and even fractal shapes often occur with many other systems whose dynamics are not connected to each other. Here, for example, we have an example for such an invariant set, which is generated by the iteration of the following rational function, Rz equals z minus z to the power of 3 minus 1 to 3 z squared, of course, in the complex plane. And as you can see, we have three types of domains, red, green, and blue, which are all mapped to one another. And these domains are all separated by some invariant fractal, on which it can be proven with quite a bit of work that the dynamics are chaotic. So, it turns out that explaining the connection between chaos and fractals is not very easy, and I would even say that mathematically it's kind of impossible. The reason being that fractals, when we think about them, are not, well, they're not a mathematical definition to begin with. However, heuristically, and especially if you happen to have some physical intuition, we can say a few things which, in a sense, explain why chaos and fractals often appear together. It turns out, at least from numeric simulations, that chaos as a phenomenon appears mostly in dynamical systems whose action on their phase space can be roughly described as a stretch and fold action. What do I mean by a stretch and fold action? I mean something which is roughly like this. Take a strip. Now, stretch it, and then fold it back into itself. If we repeat this process infinitely many times, would expect the resulting invariant set, which is, in a sense, whatever's left in place, to have a very complex shape. So this is the heuristic idea behind the connection between chaos and fractals. However, you can also see it actually in puff pastry. For example, oh yeah, I also have one here. Although, Ran, you have it next to you. But anyway, here we have a puff pastry. And when we break it open, yeah, sorry for the mess, you can see that it's separated into many, many layers. The reason being that the creation of a puff pastry is in fact very similar to this stretch and fold mechanism. Because you take a sheet of dough, you spread it with some butter or oil or whatever, and then you fold it on itself and repeat. And after you do that for a sufficiently high number of times, the structure you get within the puff pastry also begins to look slightly self-simmered. Thanks. Now, this is all nice and well. However, problem is that up to this moment, roughly all I've said is heuristics. I haven't said anything about the mathematics behind chaos. And truth be told, there is mathematics behind chaos. Most of what I've said can be rigorously proven. However, it did take a rather long time to prove it, and one of the reasons being that analyzing structures such as the Lorentz attractor can be extremely complicated, simply because we cannot do it very well. And this led two mathematicians, Berman and Williams, I think around 1978, to try a different approach. What they did was simply, what they decided to go for was sorry, I got a bit mixed up. Anyway, what Berman and Williams decided to study was basically the knots on the attractors. Why would they want to do it in the first place? Simply because some of the numerics generated by Lorentz and his successors were that many, many chaotic attractors also contained infinitely many periodic trajectories. And periodic trajectories in, say, R3 are simply knots, correct? And this led Berman and Williams to prove a theorem, which I'm about to state very imprecisely, that in a sense, any chaotic attractor in R3 contains some knot holder. And what do I mean by contains a knot holder? I mean that there exists some branched manifold to which all the knots on the attractors can be projected. And this, of course, begs the question, why would we like to do that in the first place? I mean, why would we like to study the knots on the attractors? And the reason being that, in a sense, studying the templates, the knot holders for different attractors can also help us distinguish between different types of chaos. What do I mean by that? Let's assume we have two attractors, A and B, with different templates. For example, let's assume we have one branched manifold which looks roughly like this, and another one which looks roughly like this. Okay. Let us also assume that those templates I've just sketched are topologically inequivalent. Okay, because I'm not quite sure of my drawing skills. But anyway, my point is that if those templates are inequivalent topologically, then those two attractors cannot be conjugate. That is, the dynamics on these two attractors, even though both are chaotic, have to be essentially different from one another. And this notion of essentially different chaotic dynamics can also be used to generate another mathematical theory. And it is in fact analyzed with notions from a theory known as Bifurcation Theory. And those ideas, even though they can often take the shape of rather long theorems in the theory of ODEs, can be exemplified best by some computer graphics. So just to explain the computer graphics we're about to see. Now if you could go back, thanks. Yeah, this one. So here we have a system of ODEs, which depends on two parameters, alpha and beta, okay? This system was originally discovered by a few mathematical chemists, Gaspar de Nicolas. I'm not going to go too deep into what it describes. I also can't tell you much about it. But anyway, this system, as it depends on two parameters, can allow us to consider a parameter space for the system. What do I mean by that? We can consider R2 as a parameter space in the sense that any coordinate alpha beta within R2 corresponds to a different flow defined by those equations. Correct? Great. Now, we can define an equivalence an equivalence relation on R2 by simply saying that two coordinates, alpha 1, beta 1, and alpha 2, beta 2, are equivalent, provided the dynamics they define are essentially the same, or more precisely, their dynamics are conjugate by some homeomorphism of, say, R3, or some area of a ball in R3, okay? Now, when this equivalence relation was actually sketched on a computer, the resulting image showed up. What are we actually seeing here? Here we see some infinite sequence of nested spirals, which all converge down to this spiral at the bottom. And those spirals are all, in a sense, separated from one another by black and white domains. The black and white domains correspond to area where no chaotic dynamics were detected. And the colored regions, on the other hand, correspond to regions where chaos was detected. And in a sense, the component of this partition of R2 is basically the different types of chaos with respect to the previous system. That is, the different components we see here basically correspond to chaotic dynamics which are stable in a sense. That is, they're all, if we slightly perturb the parameter in an area of a given point, these dynamics would remain essentially the same. And as we can see, there are infinitely many types of chaos within this diagram. So at this point, Noe, I think I better hand the stage over back to you.
Yes. So take a seat there. So, okay. So now we see that we have covered like some portion of dynamics. I will say again, this is a very small portion. I will present some more ideas.
Oh, sorry.
Okay, so some more ideas are the following. So there's Semereti's theorem, which is a theorem from combinatorics. It says that any large enough, which I will not define, set of natural numbers or integers must contain infinite arbitrarily long arithmetic sequences. That is, for any k, there is some arithmetic sequence in the set that is of length k. Doesn't matter what its structure is, as long as it's large enough. So Terry Tao called this theorem the Rosetta Stone of mathematics because there were many proofs for this. For example, there was a proof using harmonic analysis. There was another proof that used combinatorics. And one of the most famous proofs, and an Israeli proof, is the proof by Hillel Furstenberg, which used ergodic theory. And this is one of the results for which he received the Abel Prize. Another result that we can talk about is geometry of numbers. So in geometry of numbers, we oftentimes are interested in the following. So given, let's say that we have D linear forms, those are functions, linear functions, L1 to LD from RD to R. And we would like to understand this function, which is mu of all these things. And this mu is basically the following. It's going to be you take for any vector v in RD, you look at vi minus li of u, you multiply all the coordinates, and then you take the smallest u such that this happens. It's going to in zd such that this happens, and there is going to be such a u because zd, well, or it's going to be the infimal u, and then after that you take the supremum on all the v's. This is what's called a covering radius in a way, and this is called the Minkowski's function. Geometrically, you could view this. So this function here has many connections to homogeneous dynamics. Go on. For example, we could view this as a function on lattices. So if we look at a lattice, we say that L is a lattice. L, for example, would be the lattice which is given by L1 to LD. Then what is mu L? Let's call this shape here, it's a star shape, which is going to be given by the product of VI is less than or equal to R. So the question is, if we take this star shape and then we add it to the lattice points of the lattice, when can we cover the entire plane with this shape? As it turns out, the R such that this covers and such that for every R larger than this it covers and for every R smaller it does not cover is going to be exactly this function mu. So a question that is interesting is, for example, what would this mu be for many lattices? Turns out that you could see easily that mu is A invariant. And recall that the diagonal group A, it acts ergodically. And since this is a constant function, since mu is a function that's A invariant, it must be constant almost everywhere. So an interesting question is, what would be the generic value? And this is actually a theorem that was proven by a faculty member at the Technion. So go on. So this was actually a theorem that was proven by my PhD advisor, Uri Shapira, and he showed that this generic value is 0 in 2009 during his PhD thesis. So these are just some more ideas in addition to all of the ideas that we showed earlier. And this is a very small part of dynamics. There's a lot more to learn about dynamics. And if you would like to learn more about either these ideas in dynamics or other ideas, or you'd like to tell people about some of the dynamics that you know, then we would love for you to join our dynamics learning seminar. So it's a seminar that Eran and I will run, and everybody is welcome to join, though we will say that we do assume a background in bachelor degree courses, and we won't go over that in material because we would like to learn dynamics in general. And we'd love to see you. So thank you very much for listening, and we'd love to see you at the seminar.
Thank you, Eran and Noe.
Just a moment. One more thing I'd like to say is that next semester there will be 2 grad courses in dynamics.
Yes. So if you want to hear about some of the Diophantine approximations that I talked about, so there is a grad course, which is, I think it's 106,800. I don't know what it is. It's Nosim Betorah Ergotic. It's going to be a graduate course that Erez Nesharim will teach about Diophantine approximation. So if you like part of the things that I showed, then we would love to see you at the course.
Yeah, the second course would be, I should say here, okay. So the second course would be, by Italy, it would be about topological dynamics. It would probably touch upon complex phenomena in dynamics such as chaotic dynamics. And so for more details, I guess you can contact Erez or Tali.
And also for more details about the seminar, here are our emails. Please contact us. So thank you very much, everyone, for listening.
Thanks.